Okay, our next speaker is Dr. Brian Skerry, Global Director of Corrosion Programs for Sherwin-Williams. And he's been with Sherwin-Williams for 31 years and is responsible for product development programs and R&D functions across the globe. He has a BS with honors in chemistry and a PhD in corrosion engineering, and has authored approximately 50 technical papers on corrosion and coatings, and is current incoming president-elect of the SSPC Board of Governors, as well as having been a speaker here at our sessions several times previously. And I did find James Kirkpatrick's bio here too, so I can just mention really quickly, James worked with Brian on this presentation, and he has 18 years of rail and industrial experience and a total of 36 years with Sherwin-Williams, and is a member of RSI, NACE, SSPC, and a NACE certified coating inspector. So without further ado.
Okay. Well, good morning, everybody. I'm going to give you a quick overview of accelerated performance test methods used in the coatings industry with a focus on railcar coatings. And it's essentially what we might call a state-of-the-art update. So I'm going to give you an overview of testing methods used in the industry today. There are many test methods that the coatings industry uses. There are ASTM methods. I've listed some here for you. But there are methods that are also specified by NACE for corrosion testing, as well as ISO, mostly in Europe and around the world. And the coatings industry uses all of these techniques and many more. But when you think about it, the testing that we do really falls into two categories. We test paints for their physical properties, and we test paints for their performance properties. Physical properties might be things like hardness, abrasion resistance, and so on, flexibility perhaps. But performance properties are probably what people are more interested in the long run. How long do the coatings last for in service? Those of you who have visited coatings labs will be quite familiar with these kinds of test equipment that's out there for adhesion, flexibility, impact, abrasion resistance, standard equipment. And really, when we're looking at current commercial products or we're looking at developing new products, we use all of these techniques, and it's actually pretty easy to develop quantitative information about coatings with these kind of properties in mind. But what's not so easy is to understand or predict how well the coatings will last in service conditions in terms of overall performance testing and what to expect in the long run. When we think of performance testing of coatings, we often separate two concepts. It's weathering, durability, how long will the paints last in terms of color and gloss, but also we have to think about corrosion resistance. How are the paints going to protect in terms of rusting, blistering, delamination, undercutting, and so on. And although you might think of these two things separately, they really should be considered as one performance testing overall methodology to understand how coating is going to work. However, when we go into the lab, the weathering tests are commonly used, and in this industry we'll probably see a lot of QUV type testing. Sometimes you'll see xenon arc weatherometer testing. There are pros and cons to the different approaches, but they're all quite good actually in terms particularly of repeatability and assessments of how coatings will last for their weathering resistance capabilities. And so if you think of state-of-the-art developments over the last 10, 20 years have really been in the area of the design of the lamps that are used, either the fluorescent lamps in the QUV or the xenon arc lamps in these larger chambers. But the developments really have been to make the lamps more closely matched to the radiant output of natural sunlight. And a lot of progress has been made so that when you use these lamps in accelerated test chambers, they mimic much better the effects of natural sunlight than in the past. So state of the art, that's really where the methodology is today. Of course, there's a renewed or extended interest in actually doing exterior testing for weathering properties of coatings. And the focus in recent years has really been to go to very sunny conditions like Arizona and so on, and develop or design these test racks where the painted panels are put on the racks. And sunlight is concentrated by this methodology here so that you get very intense sunlight mixed with water conditions. Degradation of coatings really requires not just sunlight, UV, intense radiation, but also the presence of moisture. One without the other is nowhere near as damaging as both together. And that's what this kind of apparatus is intended to mimic. But there's still a lot of natural exposures that are conducted when developing paints. And these natural exposures, particularly in aggressive environments, maybe salt-laden environments, coastal environments, that kind of thing. And there's a focus really on looking at advanced test methods for assessing the degradation characteristics of the coatings, even just in natural environments. So advanced methods might be something like looking at Fourier transform infrared measurements of a coating and the polymer breakdown over time. But if you take all of these things together, you can get quite a good overall picture of the performance expectations of coatings when you're developing new formulations. When we look at corrosion, standard test methods have been around for a long time. When we think about the standard salt fog ASTM B17 method, for many years now that has been substantially discredited, and this is not a test that replicates corrosion characteristics of coated materials at all in the real life. So there's been a long-term emphasis on wet-dry cycling corrosion, and the one that we mentioned briefly before is actually the ASTM 5894 test, which combines cyclic corrosion testing with UV conditions too. So you take both together and you now have the right circumstances for mimicking what happens in real life by including cyclic corrosion with UV weathering characteristics all in the same test. This slide shows you how this methodology mimics the surface environment by using the test chambers as I mentioned. And here's an example. This is just one. There are many more. But this example shows the differences, in this case for an epoxy coating, when it's exposed to different test conditions. And this one right here is the epoxy coating after 2.5 years of actual marine site exposures. And you can see that the corrosion degradation shows large blisters on the surface that are actually filled with solidified corrosion products. And if you look at what happens in the salt fog chamber for, I don't know what it is, 2,000 hours, you don't see this effect at all. In fact, you just see some corrosion in the scribe. There's really no damage sort of further away from the scribe, and you don't see any of these solidified blisters, if you like, filled with solid corrosion products. In fact, if you tear off the paint here, it's liquid that's underneath the paint film. And these conditions are absolutely not what happens in real life at all. Just simply cycling the corrosion test does not replicate what happens either. But if you combine the corrosion wet-dry cycles with UV weathering characteristics, this is what you get. This is the ASTM 5894 test. And you can get a sense that this procedure mimics what's really happening outside really quite closely. And in a lot of work that was done, the corrosion products match the chemical composition of corrosion products in the scribes. These blisters are filled with solidified corrosion products, just like these. And what you really can't see here, but it's a really critical point, is that far away from the scribe, out here, for example, there's a significant loss of gloss for this epoxy, just like there is here in the real life, but that is not replicated in either of these two tests. So if you combine all those factors together in this test methodology, you get a good result. And it was standardized back in the 1990s by ASTM. Quick comment, the ISO organization in Europe basically uses a very similar test regime, and that's what they have standardized on for many applications, not just rail car coatings, but also oil and gas applications and so on. Now, I'll just mention very quickly that since corrosion is an electrochemical process, it's very important to try and gather quantitative information on corrosion, and we do that in our labs principally by using two techniques: electrochemical impedance spectroscopy and electrochemical noise methodology. And the importance really is that both of these methods generate quantitative information about corrosion that's taking place under an intact coating. You can't see what's happening, but you can measure it by electrochemistry. And it can be done either on painted panels, or you can put probes under the surface of a paint and make measurements that way too. And overall, the methods allow you to get an assessment of what's happening in this electrochemical interface between the coating and the metal metal so that you can assess how much corrosion is taking place on the metal substrate in the presence of a corrosive electrolyte. So a lot of information is available by using these techniques, and it helps us a great deal when we're developing new products. So in terms of state-of-the-art testing in the lab for all paints, including railcar coatings and so on, we can use electrochemistry, and we can design and develop particular methods to replicate situations that a particular customer has. We do this all the time in our labs, and if we look at the entire range of test methods available to us, when we pick and choose the ones that are relevant for a particular application, it does allow you to get a very good overall picture of what's happening in terms of performance expectations for the paint of interest and the circumstances that you have in any given customer application. So what's new? You know, there's a tremendous amount of technology development in all our industries, and it's true in the coatings industry as well. And I'm just going to give you a quick itemization that from developing new coatings, we know that regulations force change. We talked about that this morning. Fewer coats, easier to use paint, single component, and so on. But the ultimate goal is to provide improved performance and service life characteristics. Of course, this is a service life performance cost balance that needs to be taken into account. But with everything that we do, these needs, these industry trends continuously drive the need for improved testing procedures. So as far as the railcar industry is concerned, there's tremendous opportunities for different chemistries and technologies. High-performance acrylics, we talked about this morning, but many other technologies too. And again, you can see that the different technologies, polysiloxanes, polyaspartates, whatever they might be, or even the extreme using fluoropolymers, you get very different performance characteristics, but it's always a cost balance. And so you can almost obtain a paint today to provide whatever service you want, but it's always that cost balance that needs to be kept in mind when you make decisions. So my last point to make is that in a focus on state-of-the-art, the need really is to provide lab tests that correlate with field performance. We need to replicate the rate-determining steps in degradation, and we need to be able to measure and monitor quantitatively. And we have the techniques to do all of these things today. I've described some of them admittedly very briefly, but ultimately going from the lab to final performance, as long as we know what those rate determining steps are, we can provide good correlation and expectations for performance going forward. So just a quick look at what kind of information we can generate by looking at those weathering techniques. If you look at this as a schematic really, but gloss retention and color over time, we can gather information using all of those techniques or a combination of those techniques to see how different technologies perform over time. And here's just a quick schematic that shows the difference between perhaps solvent-based polyurethanes and where you can go with water-based urethanes and ultimately with fluoropolymers. And if you measure gloss and color change in the lab, sometimes you'll find changes observable in a matter of hundreds of hours or thousands of hours perhaps. But with fluoropolymers, under the same circumstances, they could go out tens of thousands of hours before you see a significant change in gloss or color. So we do have the capability, using all of these methods these days, to be able to get a reasonable prediction of performance with new product technologies that are coming on stream. I'll just mention very quickly that if we're particularly interested in measuring field correlation information on corrosion versus the lab, now technologies are becoming available where we can use handheld instrumentation, so that's schematic here, and go out onto field structures, whether it's a rail car or a bridge, whatever it might be, and generate quantitative electrochemical data that will tell you how much corrosion is taking place under a coating in any particular set of circumstances. The goal, again, is to correlate field data, practical results, with what was available in the lab when you developed the product. So, last slide. With all that in mind, and the improvement in test methods that have become available over the last 10 or 20 years, this is going to allow us to generate new products more quickly with advanced technologies. And when we look today in the paint industry about innovation that's possible, here's some examples. Waterborne systems that equal or outperform 2K solvent-borne systems. That's on the horizon. Waterborne tank linings, new polymer designs, nanotechnology, engineered surfaces, super hydrophobic, super hydrophilic surfaces, self-healing smart coatings. They're all available to us as we go forward, and the technology that's out there now is accelerating so quickly that we need to make sure that test methods are available. And of course, in everything that we do, we're focused on renewable resources, bio-based materials, and so on. So environmental compliance is a key driver for everything that we're doing. So with that, Jim, that's my last slide. So I tried to go fairly quickly to keep you guys on time, but thank you very much.
If we're doing a QUV test, what bulb should we be using to simulate weathering?
The UVA 340s, not the UVB 313s, because the 313s have a very powerful radiation band at a very short frequency range, and that destroys the chemical bonding that you'll be testing in the paint film, but that doesn't happen in real life because there's no energy in the sunlight radiation at that frequency range. So we do not use 313Bs, use 340As, which is a much more close representation of natural sunlight. In fact, I think it was one of those radiation curves was on that slide, and that's the indicator that state of the art, that's a better lamp to use.
Because the common wisdom in the rail industry for many years was that the B bulb correlated well with the weathering observed.
Yeah, well, there could be a perception, but whenever you look at published results on the chemistry of the changes in the polymer structures, and Fourier transform infrared is a great way to look at the changes over time, you'll find that the FTIR results with the UVA bulbs match what really happens in real life. The Bs do not, because the bond breaking is very different with the B bulbs versus the A bulbs. So I think that the predominance of the published information indicates that that's not the case, and that UVA is still a better way to go. Any more questions? Oh, that's it. Thank you.
Okay, then, thank you.